All right, here we go. One more example of equilibrium problems and working with ice tables. In this particular case, phosgene, COCl2, decomposes according to the following reaction, which you see there, and all ones in terms of our coefficients, so not too complicated in terms of coefficients. Kp, notice this is a pressure-based equilibrium, for this reaction is 6.8 times 10 to the negative ninth. So once again, we are dealing with a very, very small equilibrium constant, which is actually quite convenient because it makes the math a lot easier. Calculate the equilibrium pressure of all three gases if an experiment begins with 1 atmosphere of phosgene. So we're going to start by writing our equilibrium expression, and in this case, because there are no coefficients, it's fairly straightforward. So partial pressure of carbon monoxide times partial pressure of chlorine divided by the partial pressure of the phosgene itself. And then we go to our ice or rice table. I always do like to do the rice version where I write the equation at the top. No need to write that they're all gases, that's pretty much understood. My initial concentration, if I have 1 atmosphere, and I just misspoke, I shouldn't have said concentration, my initial pressures, because this is a pressure-based equilibrium, my initial pressure of phosgene is 1.0 atmospheres. And I don't need to write the units because I would be writing them over and over and over again. I'm going to write my double line here to separate my reactants from products. And if I started with 1 atmosphere of phosgene, that means that I started with none of these guys yet. All right, now the big row, the change. How are these going to change? Well, since they all have the same coefficient, in this case a 1, they're all going to change by the same factor. Now that factor is unknown, so I'm going to call that x. My products are going to increase by a factor of x. My reactants are going to decrease by a factor of x because they are being consumed. So that allows me to figure out what my equilibrium concentrations are. And I'm going to start on the right. 0 plus x is x. 0 plus x is x. I'm going to draw a line here. However, on the left-hand side, what is 1 minus x? Well, it just so turns out that 1 minus x is 1. And you're, of course, sitting there going, no, it's not, it's 1 minus x. Well, I just happen to know that because this is such a small value, x is going to be so small that even if I did subtract it from x, I would get 0.9999 something. All right? And as a result, when I round this to 2, even 3 significant digits, 2 in this problem, it's still 1.0. So I'm just going to ignore that x whenever I add it or subtract it to any number. If I'm adding or subtracting it to 0, well, now it can't be ignored because compared to 0, even a small number like 0.00001 is still going to be statistically significant. All right, so very important concept there is that ability to ignore x when adding it or subtracting it to a non-zero number. When can we do that? We can do that when k is less than 10 to the negative third. So anytime it is something, some number, any number times 10 to the negative fourth or smaller than that, we can make this assumption. So what am I going to do next? Well, in this case, I knew that my equilibrium constant was 6.8 times 10 to the negative ninth. So I'm now going to plug that in along with these values here in my equilibrium row of my ice table. So my carbon monoxide and chlorine concentrations are both x. My phosgene concentration is still very close to 1 atmosphere. And on this side, 6.8 times 10 to the negative ninth. Why did I write 19th up there? I don't know. He's on third and never mind. Yeah, this should have been a 9. No, apparently it doesn't let me erase. So I'll just go like this. Negative 9. All right, I multiply by 1 on both sides. And that doesn't change anything. So now I have x squared equals that k value. I, of course, am going to take the square root of that in order to figure out the answer. And I realize that x is equal to 8.2 times 10 to the negative fifth. At which point I realized that yes, if I were to subtract that value from 1, look at what you would get. You would get 0.999918, right? For all intents and purposes, it is still 1. So what are the concentrations of all of these values? Once again, I said concentrations, but I should have said pressures. So the final pressures are as follows. Still, when rounded to two significant digits, 1 molar. Each of these, there, and I said molar again, you see? 1 atmosphere. Each of these, the carbon monoxide and the chlorine partial pressures are going to be 8.2 times 10 to the negative fifth atmospheres. All right, hope that helps. Good luck.